I have terrible insomnia, but math is actually going to help. Here's the story. I had a doctor a while back who made a poor choice on the dosage for one of my previous medications, and once I got off, I could rarely fall asleep on my own for more than 20 minutes, and that's if I could fall asleep at all. I hope I can overcome this, but for now, I take some sleep medication so my body can get the rest that it needs. There are a variety of sleep aid medications, some over-the-counter options, and there are others prescribed by doctors. And the over-the-counter meds are not meant to be taken every night, so my doctor prescribed me another kind that's safer for longer-term issues like mine. But trying to find the right dosage has been a little tough. I need a large enough dose that I can get a good night's sleep, but not so much that I can't get up in the morning or have to fight the fog and grogginess because of the medication. The doctor told me to start with one pill, but said I could take up to a certain number of pills as a maximum, so I had some work to do to find the right dose. The natural thing to do in this situation is experiment, and that's what the doctor suggested. Start with a low dose, move up until you find the right amount. But me, being the math nerd that I am, I decided to use math to help me find the right dosage for my body. After all, mathematical modeling of blood concentration of medications is an important part of the field of pharmacokinetics, which is the field that describes the changes in the quantity of medication in various body organs over time. These mathematical models help doctors understand dosages and the duration between dosages. After all, pharmaceutical companies don't just give research participants random dosage amounts and wait until someone dies or has organ failure to know what is too much of a drug. And they don't just randomly have participants take dosages at different time intervals to find out how long is too long for toxic buildup of the chemicals in the blood. So for my situation, we will use a standard mathematical model to see if we can predict how much of the sleep medication I should take. Please understand that nothing we discuss in this video is medical advice, and you should consult with your medical professional before taking any medications in a way that's not according to recommendations. Or in other words, don't do this math at home. Okay, well, you can do the math, just don't act on it. Here's a little science about medicine. When you take a pill, it starts to get absorbed by your body in the gastrointestinal system. Different drugs get absorbed at different rates into your body. But as soon as the chemicals from the pill enter your body, the body starts to eliminate the foreign chemicals from your bloodstream, mainly through the liver or kidneys. At first, since there is more medication in your GI tract than the blood, the rate the chemicals are entering the blood is higher than the rate that the chemicals are leaving the blood, so the blood concentration increases. But eventually, as the amount in the GI tract diminishes, there's more medication in the blood, and the body removes the chemicals from the blood faster than it's seeping in, so the blood concentration begins to lower. Making some basic assumptions about the absorption and elimination rates of the medication, mathematicians developed a model for blood concentration over time. Perhaps the most popular is the Noyes-Whitney equation, illustrated here. If the absorption rates and elimination rates are about the same, then the model simplifies a little to this, and this is the one we are going to use. Putting this model into GeoGebra, notice that the graph of blood concentration over time matches my earlier description with concentration increasing, reaching a peak, and then decreasing gradually. Another thing to understand is that before the medications are effective, they must reach their effective concentration level. This takes time if the medication is taken via a pill, but it can be extremely quick through an IV. We can represent the effectiveness level with a horizontal line on our graph. This distance is the time it takes from administration until the medicine is effective. This distance is the length of time the medicine is effective. The peak represents the highest blood concentration, which is an important value since this peak needs to be below a level that is toxic for your body. Let's take a closer look at the mathematical model now. I don't know most of these values that are used to adjust the model, so I will combine all of these constants, excluding dose, into one term. We'll call it A, and try to use some empirical measurements to calculate the value of A. I'm also going to use some empirical measurements to estimate the rate here in the exponent. I can start building the model by putting in the dose of my medication, which on the pill bottle says 50 milligrams. What measurements am I going to use? I actually don't need to go to a lab and have blood drawn while I'm on the medication. Instead, I can just measure the time it takes for the medicine to kick in and the amount of time it helps me sleep. When I take one pill, I can fall asleep about 30 minutes later, and I get about 6 hours of sleep. This is not ideal for me. My body runs much better on 8 hours of sleep. This is also not a proportional relationship. If I get 6 hours on one pill, I don't expect to get 12 hours on 2 pills, or 18 hours on 3 pills. Changing the number of pills is just changing the dose, and if we triple the dose, notice that the time the graph is over the effective dose doesn't triple in length. But it does triple the peak amount in the blood, which can be dangerous. This is why a doctor might have you take a pill 3 times a day rather than 3 pills all at one time. I need to know the effective blood concentration of my particular medication. I looked it up and found a range. I picked a value that was a little on the lower end, 0.5 nanograms per milliliter. I can use my empirical measurements to solve for A and R in our model. This process looks similar to solving a system of linear equations. I will plug in values to create 2 equations with 2 unknowns. I have 2 pieces of data for what 1 pill does for me. I'm ready to sleep 30 minutes after I take the pill, so maybe that's the effective dose for my body. So when T equals 0.5 hours, the blood concentration is 0.5. And second, I sleep for about 6 hours, so the blood concentration is also 0.5 when the time is 6.5 hours, or 6.5. In actuality, the blood concentration would drop below the effective dose before I wake up. But to simplify things, we'll just work with the model for now and say that the blood concentration is 0.5 when I wake up. Here are the 2 equations. We can have Wolfram Alpha solve these for us, or we can do it by hand using an elimination technique. But instead of subtracting to eliminate a variable like the technique with linear equations, we can take the ratio of the left sides and the right sides. One variable, A, divides out, and then we can solve for the rate using the natural log. Then we can substitute the value of R back in to either equation, and we can solve for A. I actually needed to do this by hand a few times when preparing the video, because for some values, Wolfram Alpha timed out and wouldn't give me an answer. I even tried it in Mathematica, and I had the same issue. I calculated A to be 0.0247 and R as 0.427. Plugging those into our model in GeoGebra shows the approximate blood concentration for my body. I see it crosses the blood concentration first at T equals 0.5, which is the half hour, and then crosses again at T equals 6.5. This is just a nice graphical check that we have the right constants in our model. So I need to think about the curve I want. I would like the distance between these intersection points to be 8 hours and not 6 hours. The way I adjust the curve is to change the dose. So to find the new dose, I could start by changing the dose to a variable and adjusting it until the distance between the intersections is 8 hours. One easy way to do this in GeoGebra is to use one of my favorite commands, the x command. The x command takes in a point and gives out the x coordinate of the point. The y command works similarly. I took the difference in x coordinates of the 2 points so I could see the predicted sleep hours as I adjust the dose. And a dose of 85 milligrams or 1.7 pills gets me close to my 8 hours. So I changed my dose, but I experimented with 1.5 pills first. It wasn't quite enough, which is what the model predicted. I was getting about 7 hours of sleep, which is actually less than what the model predicted of 7.65, or about 7 hours and 40 minutes. After a few days of 1.5 pills, I tried 2 pills. The model with 2 pills, or a dose of 100 milligrams, predicts sleeping for about 8 hours and 40 minutes, but since the 1.5 prediction was high, this one is also probably high. With 2 pills, I had really good results. I wasn't waking up early and I felt refreshed when my alarm went off. It has really made a big difference for me to get a good night's rest. I hope you found this analysis insightful and that it shows at some level the kind of analysis that happens in the field of pharmacokinetics. If you'd like to see more videos about pharmacokinetics, for example, how pharmacists use models to know that patients on chronic medication will never reach a toxic blood concentration, then leave a note in the comments. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.